Now the next question is why refractive index is modeled by harmonic oscillator, right? These are the slides I used in my undergraduate courses before. So if you have taken my course, you have seen this before. If there is no external electric field, your neutral atom could be like this, no polarization, right? If there is external electric field, what would happen? Neutral atom can be polarized. The electron cloud would be distorted. If your electric field is from left to the right, you will have partial negative charge minus Q to the left-hand side and the positive Q to the right-hand side. Then you have electric dipole, right? Minus Q plus Q separated by distance x. This is exactly electric dipole, right? And what is the dipole moment? Q times x. And what's the direction? From minus Q to plus Q, so positive x. But this is a single atom model. In reality, we have a lot of atoms, right? So what do we need? Refractive index n is actually defined in this way. N squared equals 1 plus chi e. Do you still remember this formula from your electromagnetism textbook, right? And what is chi e? Chi e is the ratio of big P over epsilon 0 constant times external electric field. Okay? And what is big P? Big P is here. The dipole moment density by definition, which means the total dipole moment per unit volume. That is definition of big P. So if a single dipole moment is x direction, qx magnitude, you only have to multiply the number density. You can have dipole moment density. Big N means there are big N dipoles in one unit volume. Okay? So this is the formula of big P. And if you can relate the ratio between big P and the big E, the polarization density, dipole moment density over external electric field, you can have chi E, and after that you have N. So that is the strategy of analysis. But I haven't talked about harmonic oscillator yet, right? So if there is a small displacement x, so based on this model, if the x is small, there is a restoring force, right? Just like a spring. If you reduce, if you cancel external field, it will go back to this case. So there is a restoring force, of course. Okay? And the restoring force follows the Hooke's law. F equals minus Ke times x. Ke is an elastic constant. Okay? And the Ke is modeled here, electronic mass resonance frequency squared. Okay? So if you see a Hooke's law, it means harmonic oscillator, right? Any question? This picture is quite general. For any dielectric material with external electric field, it follows this way. Okay? But why there is Hooke's law? Okay, I give you one example. Two positive charges, positive big Q and the negative big Q, spaced by a distance 2d, for example. And if you place a test charge plus Q somewhere in between, what happens? You can see the arrow, right? Test charge is closer to the right charge, so the repulsing force to the left is stronger than the repulsing force contributed from the left charge. Okay? So what is the total force experienced by this test charge? To the left-hand side, right? And if your test charge is somewhere to the left, the total force is to the right-hand side. So you can easily imagine the middle point is an equilibrium point. At this position, total force is 0. Away from this position, it will be pushed back to the middle point. So the central point is an equilibrium, right? So if you use the Coulomb's law, like here, you can calculate the total force as a function of displacement, small x, which can be drawn as the blue curve in this figure. To the right, you have negative force. That means pushing back. To the left, you have positive force. Also means pushing back to the middle point, right? So this is the equilibrium because F of 0, net force is 0 at this position, and the slope is negative. This is important. If your slope is positive, this is not an equilibrium point, right? 你如果斜率是正的，那就是往右它会被推得更右，往左被推得更左，很快就跑掉了，那个就不是平衡点。所以这两个条件都要有 ，total force 0, slope negative. Okay, in this case, it's true. And although the entire force curve is nonlinear, but over this range, when the displacement is not too big, you can approximate this curve by a linear function, and the slope is the Hooke's constant, Ke. Okay, F equals minus Ke, only valid around the central region. So you can just calculate the derivative, then you can calculate the elastic constant Ke. Okay, so simply speaking, around any equilibrium position, there is Hooke's constant. You can get the constant something like this way, even like the previous page. Okay, you can have an elastic constant. Okay, now move on to the index n as a function of frequency. The polarized charge small q driven by external field E of t is governed by the Newton's law, which is very basic. The left-hand side is your total force. The right-hand side is mass times acceleration. Acceleration is double time derivative of displacement, right? What is your total force in this model? The first term is external force, charge Q times external electric field. Quite easy, right? Second term comes from the Hooke's force, restoring force, because of the equilibrium position, okay? And previously we have model, it's minus Ke times x, and the Ke is modeled by me times omega 0 squared. How about the third term? It's about friction, okay? If you have no friction, it's an ideal system, then you have the third term. But in reality, you always have friction. And we know friction force is proportional to minus velocity. The faster, the stronger the friction, right? And the direction is against your movement. So you have a minus sign here, and the velocity is proportional to first order derivative of displacement. Okay. But anyway, what's this? It's nothing but an ordinary differential equation of second order, right? How do you solve it? Maybe you know that from the sophomore year, right? Here I introduce one approach, frequency domain approach. Okay, there are different approaches. If you use frequency domain approach, first step, you perform Fourier transform for the entire equation. So Q constant is preserved. Small e of t after transform big E of omega. The second term is quite easy. The third term, you have a constant x prime, first order derivative. What happens if you take Fourier transform? You have j omega times Fourier transform of x, right? For second order derivative, you have j omega parenthesis square times big X. That's it. So after that, you can quickly calculate this result. Your displacement as a function of frequency is proportional to the spectrum of your driving field, and this is the ratio. Okay? And by this relation, you can easily identify the so-called resonance frequency, because if your driving frequency omega is close to omega 0, your denominator is closer to 0. A 0 denominator means a very big amplitude, big gain, right? So this is, you can easily tell the resonance. The last step, go back to the definition of refractive index. N squared equals 1 plus P over epsilon 0 times big E. And the P is related to X by QNX, the dipole moment density, right? Denominator is the same. And the previous page has already derived the ratio of X over E, right? Let's go back. What's X over E? You got everything here. It's a function of frequency. So we got the answer. This is the result. But remember, it's n squared, not n yet. If you want to calculate n, you have to take a square root. But this equation is already complex, right? You have j here. So this is a complex function. A complex function, after taking a square root, you have a complex function still. So certainly you have the imaginary part, n double prime, as a function of frequency. I just skip the detail, but you know how to derive it. Okay? And from here, you can calculate the gain. N double prime, K0, L. This is in general a complex function. Okay, although it's a little bit complicated, I think we have answered the question pretty well. Yes?
那它跟劳伦兹方程有什么关系？因为推到最后感觉跟劳伦兹方程
有，你把那个式子带进去，最后它就会长这个样。这个就是 Lorentzian function。一加一个 ratio 分之常数就是 Lorentzian function。只是它有一个 j， 所以就是 complex Lorentzian function。对，我没有把它全部推完。Any question?
所以说它会是一个姐姐的那原因，是因为它里面的就是 KVD 里面采集的磁化造成它的光的波长。
It's a good question. Be careful. The model we just used applies to either gain or loss. Without population inversion, you have loss. You follow a similar procedure. With population inversion, you have gain. So the only difference is the sign of n double prime only. That's it. 那你要小心的就是我怎么把 population inversion 放进刚刚那个 model 里面，以便最后我推出来的不是 loss， 而是 gain。因为那个 model 通常是被用来推导折射率 and real part as a function of frequency. Here we focus on different thing. We are interested in gain, so we neglect the real part n prime. We focus on n double prime, right? 但是 model 是一样的。Okay, we can further the discussion after the class. Okay. But my purpose is I prefer there is no miss in the slide. Although it looks a very strange result, but actually you can prove how does this formula come from. Okay. But if you accept the model, the remaining things are pretty straightforward. Here, we need to further simplify the model with the assumption if your pulse spectrum, remember, we are only interested in steady state. So the pulse spectrum here means steady state pulse spectrum. So I use a figure like this. Okay, say in steady state, this is your spectrum. If your spectrum is much narrower than the gain coefficient spectrum, which is real part of big G, shown as the blue curve here, of course, this is much narrower than omega G, okay? Then you can further simplify the complex Lorentzian model. This is the original complex Lorentzian. And if this condition is satisfied, that means omega tilde must be much smaller than omega G. So this ratio is much less than 1, right? And you can use this approximation, 1 over 1 plus delta. When delta is much less than 1, it's close to 1 minus delta plus delta squared based on the Taylor series approximation. And if you do so, what is your delta? 2 omega tilde over omega G means delta in this model, right? Then you got this. Your G, the gain spectrum, can be approximated by the constant term, linear term, but it's purely imaginary because of J symbol. And you have quadratic term. Just use the first 3 terms in the Taylor series. And this is the result. If you take real part, only the first and the third terms contribute to the real part, right? And remember, big G is in the big G. Big G, the first term and third term is G minus 4G omega squared over omega G, omega tilde squared over omega G. This is a quadratic function represented by the red dashed curve. Okay, so what's the difference? The original model, the real part of complex Lorentzian function is the blue curve, but after Taylor series approximation, the real part becomes a quadratic function, okay? From blue to red, okay? But why do we need such an approximation? At least for the central part, they are very close with each other. The approximation is pretty good. Of course, when the frequency is away from the center, the approximation is worse and worse. But don't worry, because in steady state, we have already assumed the spectrum bandwidth is pretty narrow compared with the gain spectrum. So basically within the central region only. So the approximation is okay. And if you use this approximation, you can get some advantage, okay? The pulse spectral envelope modified by the concavity and the gain medium together becomes this. The output spectrum is equal to the input spectrum times the contributions from the concavity. There are 2 terms, the loss and the delay, right? Times the contribution from the gain medium, e to the big G of omega tilde. Okay, remember, not multiply with big G itself, but e to the big G. So big G is gain spectral coefficient, not the gain spectrum itself. Okay, 它在指数哦，不是直接乘 G 哦，是乘上 exponential 的 G 次方。 And we have already know the input spectrum. It's the frequency domain representation of the Gaussian pulse shown here. And we have already approximate big G by second order Taylor series, right? And you can have the output. Okay. So what's new? You can see this, e to the G minus L, because you have e to the G comes from here, e to the G, the constant term. E to the minus L comes from here. So combining them together, you have this term, and it's overall amplification. Gain minus loss, right? If there is a positive number, you have overall amplification. If it is negative, you have overall loss. Okay? The second term, okay, e to the, this is a Gaussian function. Where does this term come from? Okay, it comes from two places. Here, you have a Gaussian function here already. And you have another Gaussian function due to the third term of the approximation. Okay? Remember, this is quadratic, but it's in the exponent. So e to the quadratic function is a Gaussian function. And the Gaussian multiplied with the Gaussian is a new Gaussian with different widths, right? So this is here. You have a new bandwidth now. The bandwidth is changed because of the third term, which comes from the gain medium. And this term usually can be dropped because if your central frequency happens to be some integral multiple of mode spacing, then this is 2 pi, the phase is 2 pi, you can drop it. It's just equal to 1. And there is one interesting contribution here. Okay? In addition to the concavity delay, big T, which is shown here, you have a delay increment. Where does it come from? Come from the linear term in your G approximation, because it's a purely imaginary one. So this term can be combined with the linear delay term in the concavity. So together you got a new delay. Original delay plus a new delay increment due to the gain medium. Okay? So it's quite interesting. The gain medium, you have 3 terms. The first term contributes to overall amplification. The second term contributes to delay increment. Third term contributes to new bandwidth. Each of them is critical. Okay? So this is the output illustration. Input spectrum, a Gaussian shape, 0 phase. After cavity and the gain medium, 2 elements. This is your new output spectrum. Your bandwidth in the future, you will see, is reduced. You got a narrower spectrum. You have a tilted phase due to the combination of concavity delay and the delay increment. And the height is modified by overall amplification. Okay?